These are the lecture notes for Chapter 2 on Part A slides. So Chapter 2 is on chemistry and Chapter 3 is on cells. They're both review chapters. They're biology review chapters. And the reason we teach them is there are concepts that you need to know for some of the chapters that we do later in A and P, but also because this information, many of you will end up taking the TEAS test or taking some type of test before you get accepted into like an allied health program. So because of that, we make sure that we teach the chemistry and the biology chapter because those topics are covered on a lot of those tests that are given, for example, especially the TEAS test. So we're going to start with the chapter on chemistry, Chapter 2, and it's divided into two sets, Set A and Set B. So we're on Set A. And this is going to be basic chemistry or inorganic chemistry. And then slide Set B is going to be the organic chemistry, which will cover your carbohydrates, lipids, and proteins. So starting with section 2.1, and this should be review, matter is anything that has mass and takes up space. So mass, which is usually measured in grams, and space or volume, which is usually measured in milliliters or cc's. Matter can be seen, smelled, and or felt because, it can be 3 states of matter, solid, liquid, gas. And weight is related to mass, but it's not the same thing. Weight includes mass plus the effect of gravity. So your mass would be the same on the moon, but it would be, your weight would be different on the moon. Okay, states of matter are solid, liquid, and gas. Then there's a section on energy. I'm going to skip through most of that and move on to section 2.2. Energy is the capacity to do work, and I'll just say real quick about energy is that chemical reactions they all take some energy. They use energy, but some chemical reactions give off energy and some chemical reactions absorb energy. So, and all chemicals all molecules store a certain amount of energy in their bonds and then release that energy when the bonds are broken. So that's mostly how energy will be covered, in this chapter is just how it relates to chemical reactions. So in section 2.2, all matter is composed of elements. Elements are the pure substances that you find on the periodic table. There are over 100 known elements, and we don't really have to use the periodic table that much. We'll refer to it, but we don't use it like you would in a traditional chemistry class. There are 4 elements that make up 96% of the human body, and they are carbon, oxygen, hydrogen, and nitrogen. And their symbols are C, O, H, and N. There are 9 elements that make up 3.9% of the body, and there are 11 that make up less than 0.01. And I guess it's going to show you those 4, and then this is the 9. Okay, so I'll cover those in just a minute. All right, so all elements are made up of atoms. Atoms are the smallest particles of an element. So 1 atom of oxygen is the smallest particle of oxygen. And so oxygen, carbon, and hydrogen, O, C, H, and N, are the elements that make up 96% of the human body. The rest of the elements their symbols are going to be calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, and iron. And you can see in this table where these elements are found. Calcium, of course, is found in bones and teeth. Phosphorus is found in DNA and also certain calcium salts. Potassium and sodium are found in dissolved as ions or electrolytes. So is chlorine, chloride ions, and magnesium. Magnesium is important for the absorption of calcium to form strong bones, and iodine is important to make your thyroid hormones, which function in metabolism. And iron is important in blood, so for healthy blood cells and hemoglobin in your blood. Sulfur is found in proteins. So then we have some other trace elements. You may not know these, you may not recognize these, they're not as important. Copper, fluorine, zinc. These are some of the metals or minerals that are important. Okay, now when we talk about atoms, there are 3 subatomic particles that make up the atom. The atom is made up of a combination of protons, neutrons, and electrons. You'll need to know the charge and location of each one. So a proton has a positive charge and is found inside the nucleus of the atom. A neutron has no charge or 0 charge, and it's also found inside the nucleus. Electrons have a negative charge. They are located outside the nucleus in electron clouds, and the weight of the electron is nothing in comparison to protons and neutrons. So electrons really don't contribute to the weight of the atom. Now we're looking at models of an atom of helium. This is helium. We know it's helium because helium has an atomic number of 2. Because the atomic number is the number of protons in the nucleus, and it has a mass number of 4 because that is the number of protons plus neutrons. As you can see, that would be 4. And then if you look at the planetary model, you can also see that there are 2 electrons because in an atom, the total charge has to equal 0. So if you have 2 protons or positive charges, you have to have 2 electrons or negative charges to balance those out. The neutrons can be equal to the protons or not. Here it's just a coincidence that they are 2 neutrons and 2 protons, but the number of neutrons does not have to equal the number of protons. All right, so we have some different elements that have different numbers of protons, neutrons, and electrons. And I can look at those numbers and tell you some things about those elements. Hydrogen, for example, has 1 proton, no neutrons, and 1 electron. So the proton tells you the atomic number for hydrogen. Hydrogen's atomic number is 1, and its mass number is also 1 because you add the protons and neutrons together for the mass number. Helium has, again, an atomic number of 2 and a mass number of 4. Lithium has an atomic number of 3 because of the 3 protons and a mass number of 7 because 3 plus 4 gives you 7. And then we have, and here you can see models of each of these. Looking at this, you can tell hydrogen has an atomic number of 1 and a mass number of 1. Helium has an atomic number of 2, a mass number of 4. Lithium has an atomic number of 3 and a mass number of 7. Atomic number is defined as the number of protons in the nucleus, and it can be written as a subscript or a superscript. It just depends on which textbook you're using and which people have different preferences for how they do that. But in our book and any information that we have from this publisher, it's going to have the atomic number on the bottom, the smaller atomic number on the bottom, and the bigger mass number on the top. So you would see for lithium, here, I'll write it. I hate writing, as I've already told you, but I will try. So the symbol for lithium would look like this, Li, and then the 3 would be on the bottom, the atomic number would be on the bottom, and the mass number 7 would be the superscript. I'm sorry, it's just really hard for me to write. I don't have a stylus, so I have to do it with my finger. So anyway, it's 7/3 is what that's supposed to say. I'll try to make it a little straighter. I'll not mess it up even more, but this is a 7. I messed it up. Okay, but that's supposed to be Li 7/3. And you just combine these two, I guess. But the mass number is the number of protons and neutrons, and the atomic number is just the number of protons. So the mass number usually is larger. With hydrogen, it's not larger because hydrogen doesn't have any neutrons. Now, we also talk about different variations of atoms called isotopes. The only difference in isotopes is the number of neutrons. So isotopes have the same atomic number, same number of protons. They're just going to have different neutrons, so they'll have different mass numbers. And the atomic weight, we don't really have to deal with that. It's just going to be the average of the mass numbers of all the isotopes. So on the periodic table, you're going to see atomic weights listed as decimal numbers. So instead of a mass number would be a whole number because it's the number of protons plus neutrons. But the atomic weight is a decimal number because it's an average. So the isotopes of hydrogen are hydrogen 1, which has 0 neutrons, hydrogen 2, and hydrogen, that 1 stands for the mass number. The hydrogen 2 is also known as deuterium, and it has 1 proton and 1 neutron, so the mass number is 2. Tritium is the isotope of hydrogen, also known as hydrogen 3, which has still 1 proton but 2 neutrons. So all these isotopes give hydrogen a mass, atomic weight of like 1 point something because it's an average of the mass numbers and their percentages. And there's a whole lot more hydrogen 1 than there is deuterium and tritium. There are not as many of those found in nature. Now, radioisotopes are isotopes that give off radiation energy. And they are used, they can be harmful, but they're also used in medicine and also used in radiation is used to keep our produce fresh. They irradiate the produce before they put it on the shelves, and that keeps our produce from going bad so quickly. So all radioactivity can damage living tissue. Some can be used to destroy cancer, so radiation therapy, but some can cause cancer. And some radioisotopes can be used for diagnosing disease. You will, if you're getting a thyroid scan, you will be given an injection of radioisotope of iodine. And everywhere that iodine is picked up in your thyroid, you will be able to see it on like an MRI or on some type of scan, so that you can tell if your thyroid is healthy or not, or if it has cancer or a goiter, or if you have thyroid disease. But different radioisotopes can be used for different types of scans to diagnose disease. All right. Now, on section 2.3, when you combine atoms, you get molecules and compounds, and molecules and compounds are just about the same thing. A molecule is a term for 2 or more atoms bonded together. So a molecule can be, for example, like a molecule of oxygen gas is just O2. 2 atoms of, oh my gosh, okay, let me try this again. O2. Okay, so 2 atoms of oxygen bonded together would be a molecule, but not a compound, because a compound has to have at least 2 different kinds of atoms. So C6H12O6, and by the way, I would learn this formula. This is the formula for glucose. This is a molecule and a compound, but O2 would only be considered a molecule. Oh, gosh, I should have looked at this and I wouldn't have tried to write it. There's O2, and H2 is also a molecule of hydrogen gas. So it's just two atoms of hydrogen chemically bonded. Now, I'm going to go over this information on mixtures, but it's not that important for what we need. A solution is a homogeneous mixture, so it's a physical mix of, for example, salt and water. Salt dissolved in water would be a solution. A colloid is going to be like your blood is a colloid. It's not going to be always. It's not what is that word? Translucent. So another example of a colloid is Jell-O, and also Cool Whip is a colloid. A suspension is like when you shake up your Italian dressing. It's not homogeneous, and everything's not dissolved evenly. Okay, so and actually they're saying that blood is a suspension and not a colloid. I'm sorry about that. Because the particles in blood will settle out if you run them through a centrifuge, which spins the blood and causes the heavier red blood cells to settle at the bottom of the tube. So that means it's a suspension. If it was a colloid, then the particles would not settle out. So we're going to start with, this is slide number 33. We'll start with slide number 33 in the next recording.